shifting, time reversal, etc. And I think we stopped at the point like when I give you a function graphically and how to represent that function as like summation of unit step functions. Let me see if I have time to do a little, let's say, exercise on the topic. Okay. All right. So let me open the whiteboard. Okay. Let's see which one of them. Last week, students level fourth. It's gonna be this one. I think this is the one where we stopped, hopefully. Yeah. All right, so this is the example. Let's see if I can grab this. It says that if you have this function and you want to represent it as summation of step functions, let me see if that will work. Okay. All right, so in the exam, expect something like similar requirements here, like you have to do some manipulations like those. You have time shifting, reversal and shifting, scaling. So, all right. So the last one was, let's say, was the one that requires a lot of work. I'll not say the complicated one, but if you get the idea, it should be easy. But how to represent this function as summation of unit steps. So as I mentioned earlier, we can divide this function into regions and you get the expression for each region. So this is region number 1, region number 2, and this is region number 3. All right, so for region number 1, if you look at it, it's just a rectangle. It starts from -3 to 0. Now, if you want to represent it as a unit step function, just recall u of t, if you draw it, just this way, and the value is 1, and this is the time. So when t is larger than 0, the value is 1. When t less than 0, the value is 0. So if you do some manipulations here, if you do time shifting, if you scale by 2, let's say, if you have 2 u of t, then this amplitude becomes 2. Now, this one here, this rectangle, imagine it like this way. So this is the rectangle. Imagine you having a unit step like this, and at some point you stopped this unit step. So how to remove this value? You just add to it the negative to it. So if this value is 1, subtract 1 or add -1. So how to represent -1 graphically? So this is, let's assume this is the y-axis. From there, you have a function that has no values, then suddenly it has this 0 value. So when you add them together, you have 1 and you have 0, the result will be 1, then you have 1, you have -1, they will cancel each other, it becomes 0. So you'll get a rectangular shape like that. Or to put it simply, the rectangle will be, you see the axis here, that's -3 at 0. So your unit steps are, one of them starts at -3 and the other one starts at 0. So simply, if you have shift to the left by 3, so you're going to be u of t plus 3 or u of t minus 3. You want to shift to the left, so you're going to be u of t plus 3. So this first part here, this positive part, it's u of t plus 3. That's going to be minus u of t. And since I'm starting from 0, so it's going to be just u of t. Now let's look at the amplitude. It's 2. So the result of this rectangle, you scale it by 2. Or if you want to express it in rectangular form, but I don't think it's necessary. If you remember the rectangular form, rect of t over t was something like this. From negative t over 2 to t over 2. If you want to represent the rectangular function as a summation of unit step, it's going to be this step function u of t plus t over 2 minus this one here, u of t plus t over 2. So that's equivalent mathematically of the rectangular function by summation of step functions. Or just to put it simply, look at the coordinates. So this one here, you have a rectangular that starts at -3. Sorry, you have a step that starts at -3, and you subtract a step that starts at 0. So it's going to be u of t plus 3 minus u of t. That will give you a rectangle from -3 to 0. Now I want to scale it by 2, so you multiply by 2. That's it. That's the first rectangle. Now the second rectangle, it starts at 0, it ends at 2. So simply starts at 0, u of t minus u of t plus 2. ولا minus 2. Shift to the right, minus 2. Are there any scaling? It's 1, so that's it. Keep it 1. Okay, now this is the part that requires work. It's a linear function. And this linear function is limited between 2 and 3. Okay. Now let's express this function and let's say as a linear function. What's the formula for any linear function? mt plus b. صح? Where m is the slope and this is the y-intercept. So how to find the slope? Just look at the values. So let's assume that you have, this is t1 and you have the value x1 and you have t2, x2. So how much is t1? 2. And what will be x1 in this case? 1. So I'm taking this point. In time, it's 2, and in axis, it's 1. What about t2? It is 3. x2 is 0. So how to find the slope? A equals delta x over delta t, or x2 minus x1 over t2 minus t1. By the way, what do you expect the slope to be, positive or negative? Negative, because the function is going down, it's decaying. All right, so what is the value of x2? That is 0 minus x1, that is 1 over t2 minus t1. I have 3 minus 2, so negative 1 over 1, that's negative 1. So you found the slope. Now how to find the intercept? Quite easy. Just substitute any value. You have the pairs t1 x1 or t2 x2. You have the full freedom to pick any one of them. So let me just clean. board. Okay, so let's take x1, for example. X1 equals m t1 plus b. B is the constant. So x1, how much? It was 1 equal -1 times t1, 2 plus b. So 1 equals -2 plus b. So b equals 3. Now my line, this function here, this line, x equal -t plus 3. Tamam? Okay, so if I ask you in real life how to draw -t plus 3, you can simply just have the coordinates. So this is t, this is x, and it's going to be something. So at 0 is going to be 3, and at 3 is going to be 0. I just draw that straight line. So it's going to go from -infinity to infinity. I want to make this function bounded in time because I'm limited between 2 and 3. So basically, if you multiply this function by this rectangle with an amplitude of 1, just multiply it by a rectangle. So anything you multiply by 1 is as if you're multiplying by something like this from 2 to 3. And the amplitude is 1. And your function is going this way. So basically, all values beyond 3 will be cancelled and less than 1 is cancelled. So this rectangle, I want to give it a representation. And simply it's going to be u of t minus 2 minus u of t minus 3. Again, that's like to put rectangles in a simpler way, just u of t minus the number here minus u of t minus the number in the right side. Okay, so we have this expression. So let's add all rectangles together. So the first rectangle, find. So the first rectangle, where's the formula? That's the first rectangle. That's the second rectangle from 1 to 2. And the third one, I have the expression -t plus 3 times u of t minus 2 minus u of t minus 3. So just combine all three expressions together and solve the algebra. Like you have, let's say u of t minus 2, it's common between here and there, distribute this one. But to me, in the exam, if you are given a function similar, a question similar to this kind of a problem, tell me that this is the region 1, this is region 2, and this is region 3, and give me the formula for each region, and that will be enough for me. Okay? Because I don't want you to waste time, do distribution here, then look for common factors of t and u of t and u of t minus 2, and so on, because you will be, let's say, limited in time during the exam. Yeah, this kind of question may come like either midterm or final, or sorry, the quiz or midterm. All right, is it clear how to deal with such questions, inshallah? Okay, sure. Okay, like if you have a rectangle like this, huh?
Oh, it's the same, but الأرقام منها negative. Like instead of 2, it's -2.
Like this one here, -3.
Why?
Like this. Like this. Yeah. So again, it's just unit steps, and then you multiply by, let's say, let's assume this is -3. U of, let's assume this is 1 and this is 3. U of t minus 1 minus u of t minus 3 by -3. Again, scaling is just a constant, just change the sign. All right, now we'll start a new topic, description of systems, or basically system properties. And this one here, like each system given to you, or we'll discuss what system is, and there are some properties in the system that we desire, like some of the properties like time invariance, That is, if there is a delay at the input, the output should have the same kind of delay. Again, just to have some expectations with the output, you don't want a variable delay or a delay different from the input. Also, we want to ensure that the system is something called causal. Causal means the system is realizable in real life. It starts like there are no values at negative times. System has memory. Let's say it relies on past values, etc., etc. All right. So what is a system? Is anything that responds when stimulated or excited by or performs a function. Usually we have a system like this. Now later on we'll call it h of t, inshallah. And here is y of t and my input x of t. This is what we call the excitation signal or the input signal. And this is the system molded by this expression h of t. So when x of t is applied to the system, some arithmetic operation happens between them. And the result of this arithmetic operation, we'll call it y of t. So the system most commonly analyzed by engineers are artificial systems designed and built by humans. The system could be mechanical, it could be electrical, it could be something digital in the computer, and so on. So engineering system analysis is the application of mathematical methods to the design and analysis of systems. In engineering, a system usually refers to an artificial system that is excited by certain signals and responds with these signals. So yeah, this is the system. It's an artificial system excited by a certain input or a certain excitation signal. So here is an example here about some mechanical systems. So you have a spring, you have rotation element here, you have some shock absorber. So that's, I believe, the chassis for automobiles. And this one here, wind rotation, that's the cup that rotates with the speed of wind. All right. So a continuous time system is a system which continuous time input signals are applied and result in continuous time output signals. Right now, all of our focus will be on continuous time systems. Remember, we have discrete times, x of n, h of n, and y of n. And whatever we apply here in continuous signals or continuous system is applicable for discrete systems or discrete signals. So we have the system here, x of t, and that's the output of y of t, and there is the transformation here. So a system with an input x and an output y can be described by this equation. So this one just saying that you apply some transformation to the input x to get the output y. Okay, so the operator h maps a function to a function, and it doesn't have to be numbers like x of t. It's just a function. So you map this function to another function there. An alternative notation, it's just like some analogy here, nothing to worry about. And it means that x will interacted with h will introduces y or produces y. Okay, so systems have inputs and outputs. So exception, okay, so something we already are familiar with. This is the block diagram. Okay, so this is an example of single input, single output. When you have, say, x1, x2, x of n, and you have y1, y2, so you have multiple input, multiple output. Interconnections of systems, when you have two systems in series, so basically you apply the transformation in sequence. First, you have this intermediate output. So that's x of t. You apply to system one, you will get x1 of t, for example. Then you apply it for the second system, you'll get y of t. So in this case, it's not multiplication, it's not addition. We'll call it just a system like a cascaded systems or systems in series. So you cannot just say x multiplied by h will get me x1, x1 multiplied by h2. It's not like, let's say, multiplication or addition like resistors in series. It's a bit different. In parallel, that one is quite easier. So you have the system that they have the same input applied to the first system and second system. The first system will produce a certain output, y1. Second system will produce another output, y2. And this is an adder, so it's just simply addition of the products y1 and y2, and you will get this is the output here. Let me open the slideshow, it'll be better. All right, so a series cascade systems connect output of one system to the input. So the overall you see here, that's y or x1, which is the output of the first system. Then that output is going to be the input for the second system. Now parallel connection is something simple here, and you have both outputs or both transformations added together. All right, so assume that you have this, let's say, a system that consists of three subsystems. Let's call them subsystems. Like this is system 1, system 2, system 3, and you were asked the output, and it's telling you the transformation or the behavior of each system. So each one here will tell you, okay, you have shift to the right by 1 unit. So my input is x of t. And this one, system 1, shift to the right by 1 unit. So when you do the shift, so here is my output. X of t shift to the right, so it's going to be plus or minus t minus 1. T minus 1. Then system 2 shifts right by 2 units. That's system 2. So I will have what? X of t minus 1 minus 2 minus 3. Now, H3 compresses by 2. Now notice the input for H3 is what? Just x of t. When you compress, what will be the output here? X of 2t. When you compress, the coefficient is larger than 1. When you shrink, the coefficient is less than 1. Sorry, expand. Shrink and compress are the same. So it compressed by 2, then H4 amplified by 3. So when you say amplify by 3, you multiply the output here. So here I'm having x of t minus 3 plus x of 2t, and both of them are applied to the system. The system is amplifying by 3, so it's going to be multiplied by 3. You will get 3 x of t minus 3 plus x of 2t. And then you can distribute, and you'll get this final answer here. All right. It's quite straightforward. I'm not sure if such question is suitable for exam or midterm, but yeah, everything is possible. Feedback systems, I'm gonna go over it real quick. That's something you will see, inshallah, in the control theory course. Control systems or control theory. So there is a theory behind it, like you are taking a portion of the output through a sensor to some certain transformation, then it's going to be added to the input. Typical examples, temperature control, water level control, and so on. So yeah, let's not worry about this one a lot. When you have multiple inputs, multiple outputs, so that's what we call MIMO. Multiple input, multiple output. So here you have two inputs, x1 and x2, and you have the outputs y1 and y2. So that's a two input, two output system. All right, symbols for block diagrams. That's something probably you'll see later in DSP or all other courses that involve block diagrams. So first you have an amplifier, or you multiply by a certain gain or coefficient. This is the common one. Like you have this triangular shape. In electronics, you call it buffer, I believe. You've seen the buffer before. So this one looks like a buffer, but with a certain constant. So whatever the input will be multiplied by a certain constant K. Here's another example here. And this one is a signal flow graph. That's again something you will do in DSP or control systems. Instead of writing the whole block here, it just like the same line, and you just put a small arrow with the number K. The summing junction or the adder is symbolized by a circle with a plus sign inside. If you want to do subtraction at the outside of that input signal here, you put the negative sign. So it means that I want to add x, because it has a positive, with the negative or the negation of y. And that's why you will have subtraction. Or it could be represented by the uppercase sigma, something like this, or just simply just a circle, and you have these signs here that will indicate this is an adder. There is also integrator, something like this, or that's usual integrators is a unit delay, TS, or in Laplace later inshallah 1 over S. So those are symbols of integrator or a unit delay, or a delay, let's call it. Those are the common elements you deal with the block diagrams. In this course, actually there is no focus on block diagrams, unlike control systems. Control systems, that will be plenty of block diagrams there. But just to familiarize you that most systems are represented by block diagrams. So an electric circuit could be represented by a system. Now remember, a system must have an input, some certain transformation, and you have an output there. So for example, you have an RC circuit that acts as a low pass filter that will pass only low frequencies. High frequencies will be eliminated. So it's a simple electrical system that is excited by a certain voltage Vn, and the response will be the output of the capacitor. It can be viewed or modeled as a single input, single output system. Here is your single input, and this is the single output. All right, and that's the behavior of the capacitor with the response of time, with respect to time. This value RC, I think in circuits you called it tau, which is the time constant. All right. All right, now let's go into the important part of this course. These properties, very easy to understand, like memory, from the name memory, that it relies on past values. Like if the system relies on past values, then the system has memory. If it does not it does not rely on past values, we call it memoryless. So it has no memory, memoryless. Causality, basically, I want the system to start having a response after 0. Invertibility, if X produces Y, is there a transformation that will do backwards, like give me Y equals to X? Stability, something very important, we'll talk about it. Basically, stability, my system behavior over long period of time, will it go to infinity, or it will decay to a small value, or will it be bounded for a certain point in time, that the system does not go to infinity after a long time. Time invariance means if the input x of t has passed through a delay system, Ts, and give me x of t minus t naught, let's call it t naught. And then I applied it to the system. That's my h. And I'll get a certain output. Now, the opposite, I'm gonna reverse between these two. I have my system, then I have my input, then I apply to my system, h. I get some certain response, and this response, I'll apply the delay to it, t naught, and get a certain another output, y prime, for example. But it's not the derivative, it's just y prime, like it's another system. Are they the same? It's just saying that if you do delay at the input, and if you do the delay at the output, will they both produce the same thing? If yes, then the system is time invariant. If not, there'll be time variant. It will become time variant, and we'll do some examples on this kind of problem. Linearity, just you can break it down into two sub problems, something we call additivity and homogeneity. And I think you've done that in circuits, superposition. You remember that? In circuits, you've done superposition. So linearity is just a superposition. You apply a certain input, x1, you get y1. And you have another input, x2, you get y2. If you apply x1 plus x2 together, will you get y1 plus y2? If yes, then the system is linear. If not, the system is not linear. All right, so let's talk about each one of them in detail. A system is said to be memoryless if its output for each value of the independent variable at a given point in time is dependent only on the input at the same time. So it does not rely on past values, memoryless. So in other words, a system with an input X and output Y is said to have memory for any real time T, T naught, there where Y T naught depends on X of T for some T does not equal T naught. So for example, this system Y of T equals X of T is memoryless because whatever point in time for the output is the same point in time in the input. So it does not rely on past values. So in this case, the system is memoryless. However, if Y of T equals X of T over 2, the best way to treat such questions, just substitute any value. So try with 4. Y of 4 equals X of 4 over 2, X of 2. So 2 is a previous point in time because my current point in time T is 4 and I'm relying on a value that was at T equal 2. So in this case, this system has memory, while this one is memoryless. Okay, another example here. So you have 2x of t minus x squared of t all squared. Notice whatever value of t here, I'm going to get the same value of t there. So this one is memoryless, does not rely on past values. However, if you look at this one, y of t equals x of t minus 1. In this case, it has memory. Because if you substitute 5, y of 5 equals x of 5 minus 1. That's x of 4. 4 is a past value because my current point in time is 5. All right, and that's it about memory, something quite basic. Assume that the system is described by y of t equals x of negative t. And what do you think the system is going to be, memory or memoryless? Just substitute any value. Y of 1 equals x of negative 1. So that's a point in the past. So in this case, the system has memory. All right, so that's the conclusion there. Assume a system described y of t equals x of t plus 4. Again, the most important part here is the value of t. So whatever value of t here is going to be the same there. So I'm not relying on any past values for t. So in this case, the system is memoryless. Let's look at this one. Y of t equals x of 2t minus 5. I will not say solve or something. Just give me an example in the exam. For example, if you put 0, y of 0 equals x of minus 5, a point in the past. So in this case, the system has memory. All right, so memoryless has a point in the present. The output should be at some point in the present. With memory, if the input is either past or future, then the output is the present. All right, so that's it about memory. Causality, I want the system to have a response like does not rely on the future. So a system is causal if the output at any point in time depends only on previous or current values of t. The input at the present or point in the past. So such system is called non-anticipative. That means does not predict the future, does not wait for values in the future, does not anticipate values from the future. If independent variable t represents time, a system must be causal in order to be physically realizable. So for example, this one, y of t equals x of t minus 1. For all values of t here, this point will be in the past. So this one is causal system. So this one is causal. This one here, let's assume t equals 2, x of 2 minus x of 3. My current time is 2, but I'm looking for a value at 3. So this is not causal because I'm expecting values in the future. Same thing here, not causal. Also, this one not causal. Integration, when you look at the integration, y of t equal 1 over c negative infinity to t. So if you want to represent it as an integration, here is the point t. and your function something like this. Integration, the physical meaning is finding the area under the curve. And you stop here. You do not wait for values in the future. So in this case, integration is causal. Is it clear how integration is causal? You only look at past values. However, if the limit was like this, y of t equal integration from t to infinity, x of tau d tau. This one is not causal. Why? Because it's waiting for future values of t. Okay, causal, not causal, not causal, causal. All right. By the way, typical question in the exam, actually in the quiz, that's why I'm covering this lecture today, is going to be covered in the quiz next week. I'll tell you what the nature of questions you're going to expect next week. So determine if the following systems are memoryless or causal. So R equal x of t. So does it depend on past values? لا. So memoryless. It does not have memory. Is it causal? It does not depend on future values, so it is causal. So in this case, it's memoryless and causal. Again, for memory test, does it rely on the past? If yes, then it has memory. Causal, does it rely on the future? If no, then it is causal. So I will not say they are reverse of each other, but each one of them does look like present, past, and future. This one here, y of n equal x of n minus 1. As I mentioned, whatever is applicable for t, it is applicable for n, or continuous is applicable for discrete. So in this one here, it relies at some point in the past, y of n equal x of n minus 1. So in this case, it has memory. Now, what about causality? Does it rely on the future? No. So it is also causal. So it has memory and causal. It relies on the past, has memory. It does not rely on the future, that is causal. Here, time reversal. If you have the value of n equal 1, you are looking for x of negative 1. So you rely on point in the past. So in this case, it has memory. Now, what about at n equals negative 1? Y of negative 1 equal x of 1. It relies on the future. So it's neither memory nor, so it is memoryless. And no, it has memory, sorry, because it relies at some past in the value, but it's not causal. So not memoryless, has memory. Substitute 1, x of negative 1. So it depends on the point in the past. So it is memory, has memory, so not memoryless. And it relies on the future, it is not causal. Y of n equal y of n minus 1 plus x of n. So at n equals 0, y of n y of minus 1. So it relies at some point in the past. So it has memory. So not memoryless, has memory. Now, there's no reliance on the future. Basically, the future, when you have any manipulations like t plus something or n plus something, it means that it's not causal. But in this one, it does not have, let's say, future values, so it is causal system. This one here is of importance because you focus only on the values of t. Now, does it depend on past values? So I have x of t plus x of t times cosine t plus 1. Now, remember, what is the focus? Is the relationship between input and output. So here is my input, and here is my output. Now, someone might ask, what about cosine t plus 1? So whatever value of t you substitute is going to result in a constant, cosine of 3, cosine of 10, cosine. So it is a constant. It does not affect the values of x. So my only, let's say, analysis should be the relationship between x and y. This one, whatever value of t, because someone might say, oh, it's t plus 1, so it relies on a future value. And then the system is not causal. No, just let's say the focus should be between the input and the output. Let's substitute t equal 10. So y of 10 equals x of 10 cosine 11. Cosine 11 is constant. So it's not I'm anticipating value in the future. No, I know it's a constant. So in this case, the system is causal. But does it rely on past values? No. So it is memoryless. So in this case, it is causal and memoryless. Again, the sine and cosine will result on a constant value. So it should not affect the function. Same applicable if you have x of t times e to the power 3t plus 5. Y of t equal x of t e to the power 3 to 5. This one, when whatever value of t you substitute, is going to result in a constant, pretty much like the cosine. So here, y of t equals x of t. It does not depend on past values, so it is memoryless. Is there any reliance on future values? No, so it is causal. Is it clear? Clear? Tamam. All right, so we've done memory and we've done causality. Now, invertibility, basically, if you have a transformation that leads x to become y. Now, is there another transformation to go backwards from y into x? If yes, then the system is invertible. If no, then the system is not invertible. So a system is said to be invertible if distinct inputs lead to distinct output. If a system is invertible, then an inverse system exists that is cascaded to the original system to produce x. So in this case, it's said that if I have an input x and I have a certain system and I produce y. Now, if I apply y to another system, which is the inverse of this one, I should get back the value x. So invertibility or the inverse system usually denoted by h to -1. It's not power, it's just inverse system. Okay, so the inverse of a system h is another system h of -1 such that the combined effect of h and h -1 will become 1. So because basically if I want to map x into x, the result of these two systems must be 1. Or basically if you want to treat it like multiplication, any number by its inverse equals to 1. But we are talking systems here, so I cannot apply this expression. Okay. So a system is invertible if its input x can always be uniquely determined from its output y. So to show the system is invertible, we simply find the inverse system. To show that the system is not invertible, we find two distinct inputs that results in identical output. So basically, to test invertibility, first, if you manage to find an inverse system, then the system is invertible. That's how you prove your point. But how to prove that the system is not invertible? Just apply two different inputs. Will you get the same output? Because you're mapping single input to single output. If two inputs will lead to the same output, then the system is not invertible. For example, x of t equals t squared. Okay. And I ask you, is this system invertible or not? All right. So what is the transformation for this function? What is the inverse transformation for this function? Someone might ask, okay, it is the square root. But the square root will lead to what? Plus minus the number. So usually square root of t squared equal plus minus t. So I'm having two inputs that will lead to the same output. Or you can say at t equal 2, x equal 4. At t equal -2, x equal also 4. So I'm getting 2 points in time that will lead to the same output. So in this case, the system is not invertible. Find two distinct inputs. I have two inputs, and they result in the same output. So the square function is not invertible. Is it clear? All right, we've done that already. So you have y of t equals 2x of t. If you want to think about it or draw the function, just simply a function with high slope crosses 0. So this is y equal to x. And that's it. It's one-to-one relationship. So it is invertible. What is the inverse? Simply y equal half x. I can just put the inverse here. So you have it here, x of t, the transformation to x of t. The other transformation, so this one you multiply by 2, you multiply by 1 over 2. And that will lead to the same output, same input. W of t equal half y of t, similar manner. So you have W of t. The first transformation, sorry, the input is y of t. The first transformation multiplied by half. You will get W of t equal half y of t. Then you multiply by the inverse system here, which is 2. So you will get y of t. And that's it. You have the input map to the output. Or you can say it's going to be 2w of t. That's going to be y of t. So you map the input together. This one here, y of t equal x squared. And again, to improve the system is not invertible, find 2 points in time or 2 points, this 2 distinct points, and show that they have the same output. So here at x equal -1, y equal 1, at x equal 1, y equal 1. So I have 2 distinct points in the input. They lead to the same point in the output. So in this case, the system is not invertible. All right. Okay, so this is the example of the y equal x squared. What about the absolute value? Is there a transformation for the absolute value? So let's say y of t equals absolute value of x of t. Is there an inverse transformation for this one? Okay. Again, try with 2 distinct points in time on the input. At x equal -1, so y equal 1. Oops. Y equal 1. At x equal 1, y equal 1. So I have 2 different points in time or the input, and they lead to the same output. So in this case, the system is not invertible. The square, I've done that already. Sinusoids in general, they are not invertible. Why? Because it's periodic function. It will always produce same values for different points in the input. Okay, so the tan function, tan x of t, it is invertible at the condition that I'm looking only at one period or one fundamental period, because the tan will keep repeating itself. Okay, that's not a good tan. All right, something like this. So the system is periodic, but if I'm saying I want from -pi x pi, if my input is bounded for one period, then it is invertible for that period. Like even the cosine for one period, for one fundamental period, is something like this. Like it will stop here. And okay, no, it's not periodic. It's not what they call it. It's not, what is the word? It's not invertible, because I have point in here and the point in there, they produce the same time. So cosine is not invertible. All right. Now, stability is one of the simple concepts here. You just look at the summation or the amplitude, and if it does not go to infinity, then the system is stable. So stability is another important property. A stable system is one of which small inputs lead to response that do not diverge or go to infinity. So usually stability, we look for bounded input, bounded output. So you cannot say my system is unstable. No, the condition for stability is if I apply a bounded input, then if the output of the system is bounded, then my system is stable. But sometimes the input itself might not be stable. That will lead to unstable behavior. So a system with a certain input X and output Y, we call it a bipostable. For every input that X is less than infinity, I should get Y to be bounded. That is also less than infinity. So this one is not absolute value, that's the magnitude. Magnitude. So to show that the system is bipostable, we must show that every bounded input leads to a bounded output. To show that the system is not bipostable, we need to find that point in the input that might lead to an unstable output, unbounded output. So for example, if you have y of t equal e to the power x of t, and think about it this way, will this system be stable or not? So as t or as x grows higher, the value of y is going to go in exponential growth, pretty much like this. So in this case, it's unstable. But if you have e to the power negative x of t, then we'll have a better system performance. Just a second. Hello? Good morning. Okay. Yeah. Farheen, yeah, she was a TA there. No, not yet. I'll finish it by this week. Okay. My bad. All right, sure. We'll do that. All right. Okay, thank you. Bye. All right. So that's it about stability. Like for let's say a large value of the input, if the system starts to increase and let's say in a very rapid behavior, then in this case the system is unstable. This one here, like regardless of the input, you notice that it converges to a certain value that does not exceed k. So in this case, the system is stable. All right. Let me see if we have some arithmetic problems related to stability. Okay. So are the given systems stable? So y of t equals tx of t. Now, even if x of t is bounded, however, the value of t is not bounded. So this one with, let's say, high value of t, the system will have, let's say, high values at y. So in this case, it is not stable because my t is not bounded. So let the input be bounded. X of t is 1. Even if this one is bounded, x of t, but this t is not bounded. So in this case, the system y of t or the transformation is unbounded or is not stable. Now, if you have e to the power x of t as an input, so if you have the input bounded for x, you have the exponential e to the power x of t. Let's say it's also bounded, even though I mentioned it's not bounded there. My bad. So this one is a correct statement because I'm going to look at x of t. If x of t is bounded, then my exponential should lead to a certain value, to a constant value. So in this case, it is bipostable. So for example, substitute a value for x of t, 1, 10, 100, whatever. You will never reach infinity in there. What about, let's say, y of t equal x of t over t? Do you think this is bipostable? Y of 0, how much? X of 0 over 0. So this one will go extreme high value, so it's not stable. Okay, you have division over 0. This one here, you have, try it this way, y of, okay, it is y of t equal tx of t. So y of, okay, you don't look at x of t here. Okay, I'm getting confused a bit, sorry. Class starts at 9. Okay. Okay, so let's go backwards. Just look for the value of x and assume a certain constant, 1, 2, 3, whatever. Then this is the value. That's like if x is bounded, then look at y if it's bounded. Now, to make it simpler, actually, if you are resulting in a constant value for y of t, then in this case, your system is stable. But if you have a function of t, then the system is not unstable. For example, you have this example there, y of t equal t, x of t. Now, assume x of t is any bounded input, 1. So y of t equals t times this bounded input, 1, which is t. So this is the function in time. And t is not bounded because when you draw t, it's a function that goes all the way to infinity. So it's not a bounded function or a bounded behavior or a bounded system. Now in here, e to the power x of t. Now x as a whole, I'm not substituting values for t alone, it's just x. So assume value for x equal 100. So in this case, y of t equals e to the power 100. That's a constant value, so still bounded, even though we think it's a large value, but still bounded, does not go to infinity. Now this one here, e to the power t x of t. Now again, assume x of t equal 100. So y of t equal e to the power 100t. So in this case, I have t here. Now, if this t goes high, then the system will go even higher. So y of 1000 will be e to the power like extreme large value there. So in this case, as t grows, then the system will grow to extreme high value, something like that. So in this case, it is not bound, it's not Bibo stable. Or to put it simply, you don't need to have, let's say, any function t, even that one, y of t equal x of t over t. So assume a bounded input for x of t, 1. So y of t equals 1 over t. We know that t has issues at 0, so it's not bounded. All right, so that's about Bibo stability. All you need to do is to assume a constant value for x of t. That's the input. And look at the expression at the output. Will you have like a function of t? Then this case, and it's not Bibo stable. If you, let's say, are getting like a constant value, then the system is Bibo stable. So it's basically bounded. All right. So there you go, the steps. Class starts at 9. Okay. So apply constant input. Just put for any value for x of t. Then check if the output. If the output is also constant, then bounded. If the system is stable, otherwise system is not stable. All right, time invariance, which is one of the most important parts here in this course, actually, to do the test for time invariance. As I mentioned, so we have delay and we have the system. Now, whether you do the delay first and apply to the system, and the other one, if you have the system, then you apply the delay. Will you get the same response? If yes, then your system is time invariant. So a system is time invariant if the behavior and characteristics of the system are fixed over time. So a system is time invariant if a time shift in the input signal results in an identical time shift in the output signal. So a system is said to be time invariant, TI, time invariant, if for every function x and every real number t naught, the following condition holds: y of t minus t naught, so that's the shift after you do the transformation, equals the transformation when you do the shift to the input, where y equal h of x. So a system that is not time invariant is called time varying function or time varying system. All right, so the standard way, we have x of t, apply it to a certain system, you will get y of t. That's the standard. Then you have x of t, apply to a certain delay, you will get x of t minus t naught. You have the delay, then you apply it to the system. You will get something called y prime of t. Now the other one, this one actually, what it means, I have x of t, I apply it to the system h, and I got y of t. Then I have the delay t naught, should be y of t minus t naught. If these blocks are the same result, then my system is time invariant. And here in the book, they're kind of assuming that you have g of t equal y1 of t and g of t minus t naught equal y1 of t minus t naught. Then that leads to h, this time invariant. This test must succeed for any g and any t naught. Here's an example, and saying that you have y of t equal x of 2t. Let's apply that card on the whiteboard. We open a new one. Okay, so my question, y of t equal x of 2t. To give you as a hint, any manipulations in t, that is time variant. So later on, when you do exams, any manipulations in t, you multiply by 2, you divide over 2, like multiplications, that will lead to a time varying system. Okay, so let's do it this way. I have my input x of t. Then I'll apply first the delay t naught. So I have x of t minus t naught. Then I'll apply the transformation h. I will get the output y, let's call it y1 of t. How much is it? So look here, y of t, the transformation, whatever inside t here will be doubled. So it's going to be x of 2t minus t naught. I shifted, then I expanded, shrink. Or that's going to be equal x of 2t minus 2t naught. Okay? Or if you want to consider it this way, consider this one alpha, like x of alpha, apply to the transformation, I will get x of 2 alpha. Then substitute for alpha as t minus t naught, x of t minus t naught, so you'll get this behavior or this output. Now the other part, I have x of t, I'll apply it to the system, h. Okay, then what you will have here, x of 2t. Then apply the delay, ts. y2 equals y of 2 of t equals what? Now someone might ask, oh, you did a shift, so substitute t equals minus t naught instead of t, then you have that. No, it's a shift for the whole thing. So it's going to be x of 2t minus t naught. Again, consider this one is alpha and do the shift. Then substitute alpha. Are they the same? No, this one is minus t naught, this one minus 2t naught. So in this case, it is time varying. Is it clear how we did it? So this is actually how you solve the time invariance problem. First, apply the shift, then apply it to the system. Second, apply the system, then apply the shift. Will you get the same result? If yes, then your system is time invariant. If you are not getting the same result, it is time varying system. For example, y of t equals x square of t. Okay. Now notice the square is for what? For x. T, there's nothing going on with t. So let's do the problem, x of t. do the delay with T naught, and you will get x square, sorry, x of T minus T naught. Then apply to the system h x square of T minus T naught. Because the square is for the amplitude. There is nothing going on with time. Similarly, x of t, apply to the system h, you will get x square of t, then apply the delay by t naught, you will get x square of t minus t naught. So they are the same, then this one is time invariant. Okay, kind of clear? Now I want you all to try y of t equal x of t plus 3. Hmm? And this is covered in the quiz actually.
I've only 2 quizzes.
Inshallah, yeah, 2 quizzes in the course, yeah. 2 quizzes and 2 assignments, I think.
Are there recording some remotely?
Yeah, I put the link. Today's lecture, inshallah, will be on YouTube by tomorrow. So the link, the lectures are on YouTube. Okay. Any idea? Do you think? Time varying ولا لا? Let's solve it. But who finished? Did you finish? Oh, guys. All right. So let's do it this way. So I have y of t equal x of t plus 3. Now I have my signal x of t. Then I have the delay by t naught, which is how much? T plus 3. So that's by 3. That's my transformation actually. So I will apply T naught. Then I will get, sorry. First I'll apply the delay, then the transformation. So the delay by T naught, I'll get x of T minus T naught, T minus T naught. Then I apply to the transformation. What is my transformation? You just add 3. So you'll get x of T minus T naught plus 3. Okay. Then the other part, I have x of t. I'll apply the transformation h. I'll get x of t plus 3. Then I'll apply the delay by t naught. I'll get x of t plus 3 minus t naught. And you can easily say they are the same. So this time shift is time invariant. Time scaling is the time varying. So when you have time scaling, there is an issue. But when you have time shift, it's no issue. Okay. Again, like whenever you are, let's say, get confused, go back to the basics. Do shift, then transformation, then to transformation, then shift. Will they lead the same? If yes, then the solution is correct. Okay. Okay, so that's another example, e to the power x of t, if the system is time invariant. So let's take it there, e to the power x of y of t, e to the power x of t. Y of t equals e to the power x of t. Okay, so the usual, I have x of t. I do delay t naught. I will get x of t minus t naught. Then I'll go to the transformation. I'll get e to the power x of t minus t naught. Then the second part, I have x of t. I do the transformation h. So it's going to be e to the power x of t. Then I'll do the delay by t naught. And notice there is nothing that will affect the exponent. This is the only thing I'm going to worry about, a over x of t minus t naught. Since they are the same, then this is time invariant system. If you look at the slides, they are doing it in a very, I want to say very weird way, but you want to assume a new function, x1 of t, and you have x of t, g. To me, I found it really hard to track, actually. So this one is not your straightforward or your, say, easy way to solve. This one is pretty much like 2t. You want to apply it. Okay. Y of t, e to the power x of t over 2. As I mentioned, any time scaling, the system is time varying, but let's confirm that. So you have x of t. Let's apply shift t naught, and you'll get x of t minus t naught. Then apply it to the system h, we will get x of t minus t naught over 2. Again, assume this one is alpha, and you'll get x of alpha over 2, then substitute back alpha. The second part, x of t, I'll apply the transformation h. I will get x of t over 2. Then I'll do the time shift t naught. I will get x of t over 2 minus t naught. Again, you do the shift for the whole thing. You don't shift this t. So in this case, we are getting different values. If you want to confirm, that's going to be equal x of t over 2 minus t naught over 2. And they are not the same. So this is a time varying system. Clear? This one here.
Yeah.
Okay, we first apply the delay. We get x of t minus t naught. Then apply this result to the transformation I have. I have x of t over 2. Now, let's assume this thing is x of alpha. When I apply to the system, I'll get x of alpha over 2. Now substitute back alpha, is t minus t naught over 2. In there, you don't do the shift for this t, you do the shift for the whole thing. Again, x of alpha, do the shift, you'll get x of alpha minus t naught. substitute back alpha t over 2. Clear? All right. So time varying and so on. Okay, e to the power x of t, we've done that. We've done similar thing here. Similarly, if you have something like this, like there's no manipulations for t, that's time invariant system. The other things are just time multiplication, scaling, and shifting or offset. So it's not gonna affect the result. Okay, so there you go. X of t, you have shift by 2. I have x of t minus 2, the transformation, or t naught. Then the transformation is there. The other is transformation, then you apply the shift. So it's time invariant system. Okay, the last part of this lecture is linearity. And linearity is, let's say, could be broken into two parts, homogeneity and additivity. However, I don't prefer to do homogeneity alone or do additivity alone. I prefer to do them together, and simply by looking at the block diagram of how to solve linearity. Basically, for linearity, I have two systems. First, I have x1 of t, x2 of t, and then I'll do it this way. I have time scaling by a1 and their time scaling by a2. Then I'll do the transformation h and the transformation h. So here you will get some certain behavior, certain response. Add them together. So you have okay, x, you have h, it will lead to y. So here, I will not even call it y1. Let's a1 transformation of x1. This one, a1 transformation of x2. And you do the addition, it's going to be a1 transformation of x1 plus a2 transformation of x2. All right, you do the addition. The other part is you have x1, add them together. You have x1 and you have x2. Okay, yesterday I covered that in the SP. I don't know why I forget what's going on. So basically, no. You have a1, then you do the scaling transformation. Okay. I think I got confused with something else. So you must have, okay, x1 and x2. Then you do the scaling, another scaling. Then you add them together, then the transformation. The other one, you do the transformation, x1, x2, transform, then you have scaling by a, then you add. Will they need the same or not? Yeah, that's it. So have a1, you have a2, you add them together, you apply the transformation, you'll get a certain answer. Then here you apply the transformation, scale and add, you'll get another answer. Are they the same? That's the whole thing. So whatever transformation, for example, you have y of t equal x of t squared. Let's say, for example, you have this system, and I ask you whether the system is linear or not. That's the whole goal of this process. So let's do the slice first, because doing it additivity and homogeneity alone. So a linear system is a continuous time or discrete time, whether it was discrete or continuous. Again, the focus is continuous right now. That has the process of ported property of superposition. So if an input consists of weighted sum of several signals, then the output is the superposition that the weighted sum for the outputs. So let y1 be the response of a continuous time system to an input x1, and let y2 to be the output of x2. Then you have it like this: x1, y1, x2, y2. So additivity means that if you apply to the system x1 and x2 together, will you get y1 and y2? That's what we call the additivity principle. Homogeneity, when you do the scaling part. You have ax1, you'll get ay1. So that's what we call a homogeneous system. All right, additivity x1 will lead to y1, x2 will lead to y2. If you apply x1 and x2 together, will it lead to y1 plus y2? So if you want to apply the additivity to the system that was provided there. So x1 of t, if you apply to the transformation, you will get what? x1 square of t. x2 of t will lead to what? x2 square of t. So let's call this one y1, and this one is y2 of t of t. Now it says, if you apply x1 of t plus x2 of t to the system, what we will get there? x1 and x2. If you apply to the system, what will you get? It's a square, so we have x1 of t plus x2 of t squared. How to that square? It's going to be x1 squared plus x2 squared of t plus 2x1 of t x2 of t. Now the whole homogeneity part, oh sorry, this is additivity. Additivity is saying that if I apply the transformation of x1 of t plus x2 of t, will I get y1 of t plus y2 of t? So y1 is x1 square, so y1 of t plus y2 of t equals x1 squared of t plus x2 squared of t. So I'm going to compare this term with this term. Are they the same? No. So we have this one, we have this one, but this is an extra. So it does not, let's say, produce or does not align with the additivity property. So in this case, the system is not additive, or we can generalize it, it's not linear. Because linearity must homogeneity and additivity together. All right, so this is the first example there for the x square. That's for the additivity. Homogeneity. Now, if you look for that one, I think it's homogeneous. So you have x1, no, not even homogeneous actually. x1 of t will lead, it's the transformation, will get y1 of t that's equal x1 squared of t. Now if you apply a x1 of t to the transformation h, you will get a y2 of t equals a square x1 square of t. Now homogeneity says if you have x1 transformation will lead to y1. If I apply ax1 transformation, I should get ay1. And here I'm getting y1 x square. Here I'm having a square. I should be getting ax1 square because y1 is x1 squared. So ay1 y1 equal x1 squared of t. ay1 equals ax1 squared of t. I'm getting a squared x1. I'm getting ay1 ax squared. So I have this one squared and this one just a. So it's not even homogeneous, the square property. So in this case, it's not even additive, and it's not The other part is multiplicative or not scaled. So in this case, not homogeneous and not linear. All right, now if you want to combine both, so linearity and LTI system, you have to apply AX1 plus BX2 to the system. You should get AY1 plus BY2. If this system does not satisfy, let's say is not satisfied, then the system is not linear. Let's see an example there. Okay, there you go. That's the block diagram. So you have x1 scaled, x2 scaled, added. Then you apply to the transformation, you'll get certain response. Then you have transformation, scaled and added, and you get another response. Will both lead to the same answer? If yes, then the system is linear. If no, the system is not linear. An example there, that's the x square. Yeah, if you want to apply both thing to the x square. So that's the block diagram I draw above. So I have y of t equals x square of t. So let's apply this block first. So I have x1. So in this case, a1, x1. I have a2, x2. Here we'll get a1, x1 plus a2, x2. This is a transformation. So here you will get a1, x1 plus a2, x2 squared. So you'll get a1 squared, x1 squared plus a2 squared, x2 squared plus a1, a2, x1, x2. So that's the result of the first block diagram. For each distinctive input, scale it. Second input, scale it, add them together, apply to the system. So this is the result I got from the first block diagram. The second one, I have x1. So here's my transformation. So that is y1, and this is x2. Oh, sorry, y1 or x square, x1 square. I have x2 square, this transformation. Scale it by a1 and a2. So here I have a1 square. So a1 x1 squared. Second one here, I have a2 x2 squared. Add them together, I have a1 x1 squared plus a2 x2 squared. Are they the same? No. So here I have this extra term and I have the square parts. So in this case, the quadratic function is not linear. Okay, so let's try with another example. Y of t, x of t plus 1. Okay. And let's see. So let's try the first block diagram where I scale, add, then multiply. So I have, if I have x1 of t, then multiplied by a1, I will have a1 x1 of t. Then I have x2 of t, scale, okay. I have a2 x2 of t. Then we add, have a1 x1 of t plus a2 x2 of t, apply it to the system H. This is going to be, you just add 1. a1 x1 of t plus a2 x2 of t plus 1. So that's the first block diagram. Scale, add, then apply to the system. The second one, apply the system, scale and add. By the way, what's your first impression? Is this system linear or not? What's your impression? Is this system linear or not? Yes? do you guys think? So yes, no question. There are no many choices. احنا متعودين انه linear صح يعني if you want to draw it will be something like this that's a line. Now let's see if this our assumption holds there. Okay, so I have x1 of t applied to the system. I have then x1 of t plus 1. Then I have x2 of t transformation by h. I have x2 of t plus 1. We scale صح? ax1 of t plus a2 x2 plus a2 a1 x1 of t plus a1 صح؟ وزعنا ال a على الجهتين. Then we do the addition. So you'll get a1 x1 of t plus a2 x2 of t plus a1 plus a2. So this one is the same, a1 x1, this one a2 x2. So they are there, but I have a1 a2 and I have 1. So it's not linear. It might be homogeneous, but it's not additive. Tamam? So yes, as a function that we learned back in the day, yeah, the function is linear, but this is the not linear system. It's not a linear system. Okay. So let's see if there is another example for linearity. So we've done the square part. Okay, the structure of the question will be the following. So actually the combination of time invariance and linearity will lead to something called LTI, linear time invariance system. All of our systems from now on, we want to, well, it will be assumed as an LTI system, but LTI systems are the more, let's say, the widely used systems because of these properties. I don't want a weird behavior in time domain when it comes to shifting and scaling and stuff like in delays. And then for the linearity part, I want to map my output to a proper mapping, my input to a proper mapping to the output. So I want the system to be my linear. So a typical example in the exam, I might ask the following. I want to check if the system memoryless, causal, invertible, and time invariant, and linear. So all these properties. Actually, remember this slide there? The first slide. No, not the first, this one. This is a typical kind of requirements for any function I may give you. Check if it's memory or not, or memoryless. Check if it's causal or not, invertible or not, stable or not, time invariant or linear. So those are the properties we check at systems. Clear? All right, so let's continue. Time is up. معناته I'll see you at 11 لأنه صح اللابتوب صح I remember. Okay. Yeah, we'll stop here. I'll meet you in the lab because I'll do the lecture, another lecture in the lab. We'll probably, let's say, dedicate it more into solving problem. Finish this lecture and problem solving. Most likely it's going to be the second week of Ramadan, like week 9. So we will be, I think, different from the other exams. 9. 10 11 I think it's better for us, we have more time to finish the course and all other midterms will be done. We have time to focus on this course. Stop sharing. Stop recording.